Hello there. So we meet again. This is our lecture number 7.3b. In 7.3a, what we have done is that we have studied or we have learned about the peculiarities of temperature distribution within grinding, and based on that particular knowledge, we have discussed how to measure the grinding temperature. Earlier to that, we were trying to predict or estimate grinding temperature. So what we have done, we all know by now that total heat flux in grinding is equal to heat flux entering the workpiece, heat flux being taken away by the grinding fluid, heat flux entering the grinding wheel, and heat flux entering the chip. Till now what we have done is that we have done dry grinding. So our QFL was 0. We have done grinding with conventional wheel, for which this was assumed to be 0. That means amount of heat which enters the workpiece is very less. Why is it less? Because the time duration is very less. Another time is that thermal conductivity of the grit material or thermal conductivity of the wheel as such, they are very less. Conventional abrasives like alumina and silicon carbide, their thermal conductivity is very less. For that, my QT became equal to QW plus QCH. So this was dry grinding. This was dry grinding with conventional wheel. Once we go for superabrasive wheel, made of CBN grits or diamond grits, then this assumption of QS equal to 0 no longer holds good. Why? Because thermal conductivity of CBN and thermal conductivity of diamond, they are much higher. For diamond it is 2000 to 4000, for CBN it is 250 to 2000, depending on the purity, crystal size and all those things. Whereas for alumina it is much less, it is 3.5 watt per meter per degree Kelvin. So QS equal to 0 can never be applied if you are doing superabrasive grinding. So today what we will do is that we will try to take a bit more complicated cases, which is dry grinding with superabrasive wheel, in which this particular term would be 0, but these three terms would be present. Only not these two terms, a third term would be present, which is QS would be present. So let us see how to tackle this. For tackling this one, long back, I believe in 1962, a gentleman called Hahn, he proposed something which is called RWS. What is RWS? I will write down. RWS is an apportionment coefficient. It is apportionment between workpiece and grinding wheel. It doesn't talk about other thing. If you have some amount of heat, how that is apportioned between workpiece and workpiece plus grinding wheel. That is the apportionment coefficient. And what was his proposal? His proposal is given here. I am going to write it once again. And please note, there is a -1 sign. Once again, this I am not going to derive. This will be using for solving our problems. So this is the apportionment coefficient. Now, what should be the ideal value of apportionment coefficient? Let us have a look. If QS is 0, the problem that we have solved thus far, your RWS is 1. That means heat doesn't enter grinding wheel. Is that good? No. If it doesn't enter grinding wheel, then it would be shared between workpiece, chip, and the fluid if you are doing wet grinding. So that is not good. It is better that QS is large. If QS is large, then the whole thing would be less. So RW would be less. So for theta to be less, RWS also should be less. So this understanding should be there. How RWS would be less? If QS is more, that means for more heat enters the particular grinding wheel. Please try to understand, for alumina or silicon carbide grinding wheel, QS is almost 0, which is bad, because then RWS would be almost 1. In case of CBN and diamond grinding wheel, because their thermal conductivity is high, RWS would be less. Please look here. If the thermal conductivity is high, then whatever is there in the second bracket would be high. That is raised to the power -1. So the whole thing would be less. So if your thermal conductivity is high, it would be less. Other things I am not explaining. This is the most straightforward explanation which relates to the thermal conductivity of the grinding wheel. Now let us take it forward. For taking it forward, we write the general equation of heat transfer. It is 0 because this is dry grinding. So this boils down to now already we have written thus so this information can be plugged in here. This information can be plugged in this equation, and this equation becomes and then you can write two equations from this. This is one equation that you can write. The other equation that you can write would be like this. This is wrong. This would be QW. Now, how do you estimate temperature? Earlier, we had Jaeger's equation. From Jaeger's equation, we have written where beta W this is specific heat, this is density, this is thermal conductivity, and this is a thermal property beta W. So in this, theta can be then written as once again there is a small mistake. This would not be QT, rather it is QW. So this would be RW, because just now we have written QW equal to this. So this would be RWS 1 minus RCH into QT divided by beta W root over LC by VW. So now you can see if your RWS goes down, your temperature also goes down. How your RWS will go down? Your RWS will go down from the basic equation if more heat is taken away by the grinding wheel. How else, from physical property point of view, how is it related? From physical point of view is RWS is equal to 1 plus 0.97 kg. Kg is the thermal conductivity of the grit divided by beta W root over RE by Vs to the power minus 1. Vs is grinding speed. RE that I have not discussed. This is the edge radius. Now, before coming to edge radius, let us come here. To reduce RWS, this kg has to be more. So, instead of alumina or silicon carbide grinding wheel, you have to employ CBN or diamond grinding wheel. Now, what is this edge radius? This is a typical alumina grinding wheel, whereas a diamond or a CBN grinding wheel would be much more sharper. As because it is sharper, this edge radius would be much less. In case of CBN or diamond, the edge radius is around 5 micron to 10 micron in that particular range. Whereas for alumina or silicon carbide, this edge radius is well above 20 micron or so. This is all for DG value of say 150 micron, that is the average grid diameter of 150 micron. So if we go back to the temperature estimation, temperature will come down because RWS is less than 1. Why it is less than 1? Because some amount of heat is being taken away by the grinding wheel. How come it can take away grinding wheel? Because grinding time is not reducing, rather grinding time is not increasing, rather it is reducing, because in case of CBN and diamond your Vs would be much higher. Despite that, because of their higher thermal conductivity, heat will enter them more readily than entering vitrified bonded alumina or silicon carbide wheel. Now let us come to an estimation problem that we have solved earlier. If I remember correctly, I might be wrong, we estimated grinding temperature of around 520 degree centigrade in dry grinding. Now we are doing the same thing, dry grinding only, but with superabrasive wheel. As because it is superabrasive wheel, this is 50 meter per second. QT, if you recall, was 70.8 watt per millimeter square. LC was this, BW was this. So now we have to calculate RWS. So for calculating of RWS, let me write down the equation. And here I will use a different color because here these are the new things that are incorporated. One is kg. This kg, let us take it as 400. So this is a CBN wheel for which this is grinding steel. Thermal conductivity of CBN has been taken as 400 watt per meter per degree Kelvin. RE has been taken as 5 micron. And Vs in our earlier examples was 30, but here as I am using a CBN wheel, I can work at 50 meter per second. So this is 5 into 10 to the power minus 6 into 50. So please calculate. Let me also calculate RWS in the meantime. So let us get the value of RWS. My calculation of RWS is giving me a value of 363. I hope you also get the same value. and then let us proceed and solve the rest of the problem. For solving the rest of the problem, this was theta equal to 1.13 QW divided by beta W into LC by VW. So this becomes theta equal to 1.13, which we have just derived, 1 minus RCH divided by beta W root over LC by VW. In our previous calculation, RCH was rho W CW into theta MP divided by UG, and I believe, I am not very sure, but it was in the range of this. So I will take this particular value and proceed. Maybe in our actual calculation it was slightly different, doesn't matter. So this number becomes 1.13 into 0.363 into 1 minus 0.25 divided by 13964 into 3 into 10 to the power minus 3, that is the contact length, and divided by 0.2 meter per second, this is VW. In this expression, one particular term was missing, which is QT. So QT has to come, which is 70.8 into 10 to the power 6. If we calculate this, then we will get the estimated value of theta. Let us do that calculation. You can also carry out the calculation simultaneously with me. Let me also do the calculation. This value is coming out to be 191 degree centigrade or Kelvin, because once again I must tell this is temperature rise. The workpiece temperature would be temperature rise plus ambient temperature. So here you are just simply calculating the temperature rise. So what have we got? We calculated theta dry. We calculated theta dry with CBN wheel. This was calculated using two approaches. One was Malkin's approach, another one was generalized approach. Both of them, they give similar temperature, which was around 520 degrees centigrade, which is rather high temperature. When you employ CBN, then it drastically reduces to 191 degrees centigrade. You did not change anything. Despite that, you got some benefit. Now, there is one more thing that I will try to bring in, which I avoided earlier. What is this QT? QT is the total heat flask. Let me get some other color so that we can write it. QT is nothing but grinding power divided by LC into BW, which is nothing but UG into A BW VW divided by LC into BW. Forget about this term for the time being. Let us concentrate on this UG. What does it have in UG? You have ploughing, you have primary rubbing, you have chip formation. When you are employing CBN or diamond, they are much more sharper as compared to alumina or silicon carbide. Their edge radius is much less, because of which these two terms would be much less. So when we have used QT equal to 70.8 into 10 to the power 6 watt per meter square, we avoided some further calculation. Okay, we avoided some further calculation, but actually this number will go down further. It will go down further a lot, and ultimately this temperature will go down. So here I am trying to mix technology and theory. The name of the subject is Theory of Abrasive Machining. We are studying the theory, how to estimate temperature, but here comes the technology part as well. Where is it coming? If you employ superabrasive wheel, then the technology part is coming. If you employ superabrasive wheel, they are sharper, they can be employed at higher speed. If you do that, if you go for higher speed, then the chip load per grid goes down. As the chip load per grid goes down, UG or the force requirement also goes down. This is one aspect. As because they are sharper, then ploughing and primary rubbing component goes down. UCH doesn't change, it remains there. So what you have is that you have a drastic change in your grinding situation. Grinding is characterized by high grinding temperature, which is the root problem in grinding. It leads to thermal damages, surface cracks, subsurface cracks, tensile residual stress, burning and whatnot. But if you employ superabrasive wheel, with lot of simplification, we have calculated this temperature as 191, but actual temperature would be further less. So that completes lot of material for us as far as grinding temperature is concerned. So for that, let me go back to the previous one. So maybe what I'll do is that I'll go to a fresh slide and try to explain it. I'll go to a fresh slide and try to explain it. So QT equals to QW plus QCH plus QS plus QFL. So this has been taken into consideration, this has been taken into consideration, this has been taken into consideration. And the equivalent technology is dry grinding by superabrasive wheels. Is it used in industry? No. Then why are we doing it? Because we are trying to approach the final one where QFL is not zero. Till now our QFL is 0. We do not want that. So QFL should not be 0. That would be our next part of the lecture. Today I am not going to address that. Today the next thing, let us see what is there in the next slide. Next slide is an assignment. This assignment has to be submitted by email by 30th October 2020. To which email address it has to be submitted, you will get that particular information through Microsoft Teams. The whole assignment has to be handwritten. After that, you take a photograph of that assignment with your mobile. If you have a scanner, which is unlikely, scan it. If you do not have a scanner, take a photograph, transfer that photograph to your laptop, convert it into a PDF document, and then submit it by email. And the most important thing is that assignment has to be handwritten. How the assignment is different from what we have done? Okay, so let us see how the assignment is going to be different. So there would be two assignments. This is A. Let there be only one assignment. Vs equal to 50 meter per second, and this is this. But only thing what you can look here is that in the previous case our U0 was 210. Now I have given you a U0 of 140. Why have I given that less? Because we are using a CBN wheel for grinding steel, and that is less because that is less because we have less chip load, because we are working at a higher speed, and there is less ploughing and rubbing. So thank you so much for your attention. This is the last class before our Durga Puja holidays. We will meet after the Durga Puja holidays. I will extract the holiday list from the institute website and submit in our Microsoft Teams channel, so you will be able to know when the next class would be. Thank you so much. Thanks a lot for your attention. We will meet after Durga Puja.